Lots of traffic.
We need that material. This is another thing we will see. I guess we can discuss this quickly tomorrow or if we decide. This kind of thing will be not next time.
You're not using it? Okay, I thought you were using it. Wanted to know if everything's going fine. You use it? But sometimes they are bugs or so, and you keep so, and then we know, and you keep on display, keep on moving, and everything is fun. Releasing new versions, but often people contact me and we fix it, we send me updates. Depending on how many people
exciting topic. It is about uncertainty and traceability. I'm sure you're all thrilled to hear about this. But I'll let you know why you should be excited. So the aim is, and this actually ties in nicely to the talk we heard in the last session, particularly by Clement here. It is about multi-sensor data fusion. It also ties to timelines of the working group. How are you going to do this if your sensors are drifting over time? And of course, traceability is one way to tackle that problem. Uncertainty is another thing. Uncertainty helps you in analyze your data and reach a better understanding. So the two are quite tied together, traceability, uncertainty, and we are trying to do this like back to, I think someone already mentioned it, ISO standards. Back to the definition of power. That's what we measure, like reflected solar energy. And so that we need to bring out of the laboratory and all the way. Never mind the task plan here. So number one is we're going to synthesize the knowledge. We've got a little questionnaire which I will badger you to fill in after we've been through the talks. And this should give us a view of who uses what sensors, what kind of wavelengths, how many bands are you going to broadband or hyperspectral, and how far have you progressed along the route towards the holy grail of traceability and uncertainty. So that should give us a view, which will tick objective one and also deliverable, finally, that we compile this. Then we are going to establish best practices. It's very clear that we cannot visit every one of you and implement the full traceability chain for all your little problems you've got. So we are going to find a solution for a more like generic. We'll probably select one sensor that most of you hopefully use, which we'll learn out of objective one, and then create an example of an easy example which we'll use in a training school, how to go about calibrating a sensor, establishing some uncertainty budget, and pushing this through towards a simple, in collaboration with the working group, one selected application or a high-level product. So that is, that'll be part of this training school, and that'll give us these practical examples. Then, what else is here? Software support. So the examples we're going to provide is we are handing out these examples as code. So you can use that as a basis. And on my side, I will also work on upgrading my spectral database to handle uncertainties, which is on the route towards supporting this through software. Okay. So here we've got the program. So I just gave the intro, what we're trying to do. Now for something more exciting, I'll start with a bit of a nice story about field spectroscopy. Then we'll hear more about instruments, about temperature effects, about how to install the flocks, sensor characteristics and influence in fluorescence. So it all kind of plays together. It touches actually every other working group. Okay. So now, I've been sort of drifting off into calibration after my master's degree, and I started to do airborne calibrations and doing lab calibration and always trying to collect ground data to calibrate and validate my airborne sensor. And I did this for too long a time. I worked on uncertainty in the laboratory. I tried to push it at least to the radiance level. This is as far as I ever got. And so 10 years of doing this, sort of you lose the contact to the actual problems when you sample nature as it is and its complexity. So recently I've spent a bit of time in Australia. I got involved in the Lord Howe Island weed eradication program. This is an island, it's about 400 nautical miles off Sydney, the east coast of Australia. It is a restoration effort. The ecosystem is to be restored to hopefully its original status. It's a 30-year program, we're in year 12. The sort of targets achieved have been all the feral pigs, all the feral goats, all the feral cats have been removed off this island. The rats are going to be targeted this year. In parallel, there have been plants removed. There's a few invasive species that have really taken over the ecosystem. 2 million plants have been removed off this island. And now we are moving into the next stage. The question is how to monitor this long term, how to find the different pockets where these weeds still exist. And the terrain can be somewhat difficult. As you can see, this is the topography of the island here, sort of a flattish northern bit, and then you get these two peaks here, over 800 meters. They rise out of the sea within less than 2 kilometers. You go up towards this cloud forest, which is of interest due to also climate change research. And now the weed program must cover the whole island. And of course, in particular, the area in the natural park towards the south of the island is a quite tough environment. Now, the mission we got here is collecting spectral ground data, getting a library, figuring out can we actually separate these weeds. This is a sort of a preliminary analysis to inform us can we use imaging spectroscopy from drones to later on map larger areas. It's been the toughest terrain I've ever crawled through with a field spectrometer, and it involves also bush bashing and rock scrambling. It's been a brilliant adventure. You get to see wonderful coastlines. You get to sample these invasive species right next to a crumbling cliff line. And while you do so, you start to question how well is this going to work. I want to detect the weeds, I want to separate all these species. This is what we're dealing with, part of the canopy. And I mean, I want to allude to your talk before. We can already see by the naked eye there's color differences, but also structure. And it's a closed canopy. And fair enough, a lot of species intermingling going on. After a few days in the field, bang, spectra per species. There you go. And what you really, at first glance, it's very obvious that most of these are plants, right? and that is already the first shock. There's one outlier, which is this one down here, which is a grass that is usually pretty dry, and therefore you can see that how lucky can you be and what can you hope for. So here's a few thoughts about uncertainty. Where could it be? First of all, there's limited chance to collect enough stuff. Very limited in terms of analysis. Furthermore, target homogeneity. I mean, look at this. So, like, you've got this brilliant idea of, oh, there's going to be this shrub, and next to it is this other shrub, and we're going to separate them, and it's all going to be hunky-dory. But now these species are intermingling, you've got a lot of shadow, so you bush bashing to this location, you're measuring this, and while you look at it, you go, what is this going to look like in a few hours when all the angle changes? And there's going to be a different play and the interaction of shadows and leaves. Then, as always, on these islands, you've got the cloud build-up. And this we all know that the ideal conditions don't exist. how do you deal with the irradiance conditions? And also in view of the future drone flights. Now that's a single species I've picked out, and look at the variation. So is that supposedly you want to use that to classify it? And that's what it looks like. That's what I said, it's the structure. I highlight the structure. To me, the structure is a major part of what we actually see in the spectrum. Of course, the guys on the island were saying it didn't rain for 2 months. So maybe there's also a drought condition, but probably you can't even see whether it's a drought with all these other effects going on. BRDF, solar angle dependence therefore. These are certainly the big sources of uncertainty. But there's also instrument-related uncertainties. That is a plot I took from Alistair's paper, a wonderful work on where actually a spectrometer does look like in its measurement support, and then combine this with the hopwood, which has like these pretty erectile leaves. So like you're looking on defined spots within the field of view onto a canopy that's mostly, let's face it, shadows and woody material. So there's an instrument effect you're going to get into your measurement. There's also, as we could show, a temperature effect in these instruments, which lead to these little jumps in between the detectors. We can correct for temperature, but it could also be the field of view effect. Now, talking about one of the more important sources of uncertainty, that's of course the irradiance. How do we measure the irradiance? I've been here in the field with the guys from NASA JPL at Ivanpah, wonderful place, super flat, super clear skies. You've got all the time to set up your experiments, everything is level, you can walk this fantastic homogeneous place. Great. Okay, then you're in the field, you need to carry everything. You try to look at the concentrated face here of my colleague. She's trying to level this panel, while I'm trying to also keep an eye on the clouds. We've got a very smart little system here that's got a bubble level on it. You do what you can, right? Talking about reference panels, they're supposedly all white, and they do look pretty white. So I took them out on a little tray one of these days and I measured it, and we also did it in the optimized cost action in Machadas. So here's a nice little plot to shock you. It's like a brand new panel versus an old panel. You can see it drops like here in the UV blue, that do 20% difference. So if you weren't to calibrate that one and compensate for the biases, you will be really in trouble. In particular, if you want to do timelines, your spectrum panel is getting soiled over a field season. You're going to have a wonderful little kind of change, a drift over time, which is purely due to your wrong irradiance measurement. So I did like a little test here at Uni Melbourne. These two panels, one of them is the lab and one of them is the field panel. I cannot really say which one it is. Anyway, so I'm doing a little uncertainty budget. Blue line here, calibration you get from Spectral on. Then I'm adding Spectral aging, which I took from our experiment in Zurich. That's just the mean kind of deviation over time. Then I'm combining the two, simple summing up the squares. What else? Oh, angular uncertainties. So there's a common misconception quite often that it's catastelite, more or less Lambertian, but it must be level. So I'm putting in a 1% uncertainty of like leveling accuracy, and I'm adding this to the data. So now I've got system like laboratory calibration uncertainty, angular error, and aging. So that is my uncertainty budget. Let's call it 2.5%. Anything missing? Did I miss something? And it is Lambertian, we see. It is Lambertian, but that's only a theory. So here, sinus angles. So like that's a measurement in the laboratory a few years ago at the ESA ESTEC. You can see that depending on your sinus angles, I believe it's the data, so I didn't do it. But as an example, it'll suffice. So I took the Bidu-Busch reflectances, and the reason why they look so fat is, sorry for that, I put on little error bars. So I zoomed in here. You can see this is without uncertainty, and then it fills up this space essentially. So is this like, why should I do this? I haven't really tested it, but it's my belief that we can do some machine learning and testing using, for example, these inputs as like probabilistic a priori information. There's algorithms that require uncertainty, so this could be one of the inputs. You can probably get a more robust machine learning result if you add a bit of sensor noise. I'm talking about sensor noise. Here I got two variations of how I can add noise to spectra. Are there any feelings in this room? Which of these two, what could be the difference here? Why would I do this?
Lower of averaging?
There is, the reason why I'm asking is like, here I added random noise, and here I put on full correlation. The random noise, I've seen the random noise in quite some machine learning papers, which seems a great idea, but these people never use the spectrometer. You never get a spectrum that looks as noisy as this, at least not out of my spectrometers. It's always somehow biased, but it still looks clean. Probably the full correlation is also wrong. The truth will be somewhere in between those. So the question to ask is, what is the spectral correlation length, such that we can use better modeling of noise in the future. Final thoughts on uncertainty. So like instrumentation, I looked at this, like instrument temperatures and linearities. Javier in his talk will touch on quite a few of these. But then there's all these others. Uncertainty of the structure and the BRDF, so probably we should invest in other sensing technologies. This is why I'm saying multi-sensor approaches, hooray, to the rescue. We need just more information to parameterize these systems. Scaling, so again, we need field experiments and then upscale it, and we need the RTMs to do so as well. Irradiance. I think irradiance is a really tough one to measure. There's many things that can go wrong. And if you get the irradiance wrong, your reflectance is wrong. Operator. It seems surprisingly simple to use such an instrument in the field. I want to use the training school to do a repeated experiment with different operators and just see what we get. Also, sensitivity analysis regarding the sampling protocol. And here it's like, how do I place the sensor in the field? How is this going to impact my results? So here RTMs can help. There's these machines where you can kind of simulate whole scenes, and you can just place your sensor and your operator wherever you like and see what happens to the whole radiation budget. And time series models, here we go again. Okay, that was like my biggest worry. I'm there in the field for a few days capturing these R. Maybe we are tackling the wrong ones at this point. And of course, new algorithms that will require probabilities. And so probably you've all been waiting for the results. User accuracies using random forest, just cutting out the noise, nothing special here. So probably if you fiddle with the data for another few months, you could push it to 80%, but hey, who cares? What really matters is whole spectrum, 78, because we want to fly a UAV-based sensor, VNear. So we go to 74. so there's not so much information in the sphere here. Interestingly, like we did, like the guy who did the analysis just cut it at 850 or something instead of going to 1000, and there is a lot of data in this last bit of the veneer. So there you go. That should give you a bit of an idea of exciting things to do on island conservation and also related to these uncertainties we should consider. Any questions? Yes, please.
Thank you for the presentation. I would like to ask two questions. The first one is very simple but very important. Can you offer a method for cleaning the panels?
Cleaning the panels.
Doing the measurements,
Yeah.
inspect the other things.
So what you can do is you can grind them with a sandpaper. It shouldn't be a fine sandpaper, because if you get a too fine sandpaper, you actually polish the panel, and then it'll be a specular reflection. So it's got to be a coarser kind of paper, and also do it under running water, because it's Teflon based, so you shouldn't grease that. It will give you trouble in a few years' time in your lamp.
I think there is a document from Spectrum with specifying also the grain, the exact grain that they want.
Yeah, there is. The other thing I should probably mention is that what a good practice is, what I will push towards in the next few years here, is to monitor your spectrum panel over time. That is, if before it goes to the field and after it comes back from the field, go to the lab and you've got your pristine spectral lamp sitting there, and you figure out a protocol how to measure the two. And first of all, figure out when to clean it, and secondly, get yourself a correction factor to correct for the bias. And it will be an interesting little research to see how quickly the dirt builds up and in which wavelengths, like usually the blue ones are the worst ones. And second question, yes please.
Do you have a conversion method for the measurements made at different times of the day? For example, conversion them to the standard sun angle, for example, 45 degrees like this. Because only you have one chance to measure at that standard angle through the day. So we are making these measurements different times of the day. So
well, my guess is that really the crux to it is to develop a BRDF model, but I don't know who said it, but we didn't hear much about BRDF. BRDF studies been big like 10, 15 years ago, and now there's a lot of papers who kind of just use like MODIS kernels and are happy about it. Personally, I don't believe it. I mean, it's just an approximation. If I use a MODIS kernel on these vegetation spectra, it's not going to mean much. Because like the inherent structure, every shrub has a different structure and leaf orientation. Even intra-species is going to be already hard. But like the BRDF study, like we had from Jülich, Andreas Porter had this flying goniometer. I thought that was super cool. No one's really picked up on it, but it would be. I think it's essential to have the BRDF.
Yeah, maybe more comments. I'm afraid I'm one of these guys that adds random noise to the spectrum for machine learning applications. And indeed, we are aware of it, and we struggle also with it. We know that we make the spectra way too spiky, and it doesn't make too much sense. And so we struggle with it. We search for alternatives. Typically, we smooth out our noise, but at the end, we have to know what's the amplitude of the noise and what would be the smoothing window. So I think this would be really an interesting topic for studying within this working group. But many people struggle with it, and we can come up to guidelines on ideal use of noise and spectral data.
Yeah, I totally agree.
Doesn't this, let's say, go back to the characterization of your spectral system in the end? Because I mean, you're applying your machine learning technique to a specific spectral system each time. So couldn't you include properly, let's say, the specific noise, for example, characterized for each system?
Often we want explicitly make the data more noisier, especially when we use simulated data, right? Because we want that our simulated data looks a little bit more like natural conditions, and for that reason we add noise, that it looks more like reality, to say. But we know that just adding random noise doesn't make too much sense. So these are questions, I think, for
yeah, these are the open questions, are like a noise generator that is like adding system noise, but also like these kind of biases that are like not like between band, that the ones that are correlated between bands. That kind of uncertainty that must be added as a, well, it is noise, but it's just not such a random noise. So that should be added if
Which
you want
process should produce a correlated noise?
It is like, for example, temperature effects. I could see that somehow the whole thing. Maybe Javier can probably expand on this a bit.
I guess there are, I mean, for sure there is some kind of random noise and there is some randomness in the signal, but part of the noise maybe is coming from sensor responses. And these responses, I mean, if you're not with some uncertainty, so you can always basically add uncertainty to the parameters of the models. I mean, not to directly to the signal, but you can add noise to the parameters of the models that are simulating these responses, and of course you can account for the covariance of these parameters. And then maybe this is what actually is adding biases, which are not as noisy and spiky as other, but they can still carry some noise, because maybe, I don't know, like the directional response of the cosine receptor or the spectral panel, I mean, depends on the diffuse and basically the direction of light, and this obviously has included some noise, so it's not only the, let's say, it's not that it's adding only random noise, there is a bias, but also this bias brings a smaller portion of noise. So maybe models can bring this noise together with the bias. But
yes, it's like the spectral uncertainty. You saw it's like in the, let's say, if you buy the new, you've got like 0.5% of uncertainty. Well, how do you model this uncertainty? It's not like noise. It's actually a shift. It's like the whole spectrum shifts up and down. But so what I did, but this change will again be wavelength dependent. And at some point, if you get detectors built into the instrument at the detector boundaries, that correlation will break down to a certain extent because it's independent chips. But yeah, so I haven't got a solution I can hand to you, but I'm just saying that we're working on it.
Actually, maybe I missed that part of your presentation where you showed the spectra, the number of species that they were looking like, and I didn't understood at that moment that these are measured at the leaf or at the canopy level?
At the canopy level.
At the canopy
Yeah.
level. So, okay, so we assume that there are a number of crop or fluctuation, let's say, physical or chemical parameters that are affecting this spectra, and I would like to know which one did you measure with these species? I mean, did you only measure the spectra, or did you measure also these basically properties of these canopies, and then you saw that also these properties are also in the same range, or they were?
No, it's just canopy measurements, spectral canopy measurements. There is no other biophysical measurements taken at this point.
Because basically I assume if these properties of these canopies are also along, I mean within the same range, then what you showed makes sense. Because basically if these biophysical or biochemical properties of each canopy are somehow similar or within this particular range, then I would expect that something like that.
There is that. I still believe that if you were to measure single leaves, they would all collapse almost into one single spectrum. The big impact is the structure. The structure is just shocking. Yeah, but it's yeah, I guess so. Yeah, I mean we had some, maybe I'm prolonging here, but one comment on this, like we now have these like tree models where you can like take off all the leaves and we can stick on other leaves and put it in dart. And what we did is we had like a tree and we put on beach leaf optical properties and simulated it, and then we stripped them off and put on leaf optical properties out of the tropics. And it didn't change much. Yeah, either the leaf optical properties and the specular diffuse components are wrongly modeled, or the main signal is from the structure. And I think the answer is somewhere in between.
Yeah, okay. The reason I mentioned this because I did some spectral measurements of different species at the leaf level at different time, phenological time, let's say. And of course there are differences. So depending on the chemical, I mean just at the leaf level, depending on the basically content. So there are differences, but I was,
They can be, my belief is they can be overshadowed by structural effects. And anyway, we'll carry on here. So we've got Laura here. Yeah, Laura is on the floor again. She is going to talk about calibration.
That we all agree that vegetation is very important in our life. As we notice, because of that we are here, I suppose. It's giving us the oxygen, it's giving us the food, and because of that we are trying to monitorize the effects from the ground up to the satellites. And how we can monitorize these effects, one method is to see the interaction, to study the interaction between the vegetation and the sunlight. And two signals that can be very useful in this direction are the reflected vegetation reflectance and the chlorophyll fluorescence. And which one is the most challenging, in my opinion, is the chlorophyll fluorescence. And why is that? Because practically from the entire energy that the plant is taking from the sun, only 2% is going to this cycle. So my talk today will be focused on showing you some aspects related to methods for characterization or calibration of spectrals from the spectral point of view of field spectrometers, and mainly what is the difference between using different kind of configurations for these spectrometers. And why is so challenging to measure fluorescence is because, as you can see in this graph from the paper of Phenology, you can see that the reflected signal practically is almost covering the fluorescence one. So it's very difficult to separate between the two of them. To be possible that, it will be very important to have very well characterized or to have a very good knowledge on the spectrometer that we are using. So some configuration that was suggested in the paper of Copo, published in 2017, it's this presented in this table, and as you can see, the challenge is coming when you have to measure the SIF in these oxygen bands. And why is that so challenging? Because you need a spectrometer, an equipment to be used having spectral sampling interval below 0.1 nanometer and the spectral reflectance below 0.3 nanometers. So there are not so many instruments with these capabilities. Just to show you a classical example of the internal configuration of field spectrometers. Practically, the internal configuration of a spectrometer is similar with this one. Practically, the light from the leaf is coupled to the emitted or reflected one. It's coupled in an optical fiber, inside of the spectrometer. The light is passing throughout a slit, having different width. The light is reflected on mirrors that it's also reflected on dispersive element. That can be a prism or a grating. Generally it's used gratings. These gratings has a different number of grooves per millimeters. And this separated, practically the grating is separating the broadband light in pieces. And this separated light is reflected in a detector. So, related to spectral configurations and spectral resolution, the changes in this spectral resolution is given practically on some parameters that it's given. This changing in spectral resolution is the slit width, the number of the grooves per millimeters on the grating, and also of course the sensitivity of the detector, the number of the pixels of the detector, the distance between them, the numbers of arrays, and so on. So you can see here an example of spectra measured for the spectral range nearby the oxygen bands, A and B. When you are using, for example, different kind of slit width. So practically using different slit width, you can obtain this variation in full width half maximum. Full width half maximum is given in its good relation with the spectral resolution. And this is not the only difference. You have also difference in the central wavelength, and you can see that it's not linear, and it's very different and it's not linear. So practically it's very, very important to know the configuration of your system and to know if your configuration is corresponding to what you want to measure. Because, for example, if you are using, let's say, a configuration that gives you a full width half maximum of 1 nanometer, you will not be able to measure correctly the signal from the fluorescence. Within this cost action and the optimized action was frequently used, this system, Piccolo system. And what is the advantage of this system, I would say, is this combination, total combination. It's using two spectrometers, one having lower resolution, spectral resolution, and one and it's used for reflectance measurements, and one having higher resolution, spectral resolution, and it's used for SIF measurements. And also one good advantage is that it can measure simultaneously upward and downward radiation. So in the same time you'll have radiance and irradiance signal. But can be an issue if practically, so you have here two fibers having, let's say, 400 microns diameter, and the signal is going from one fiber to one spectrometer and the other one to the other spectrometer. In this case, you have a fiber having a larger core because you need to couple as much as possible signal. So practically, again, two fibers having 600 microns diameters is going to each spectrometer. So at the end, here, you'll have this kind of structure. So practically, you'll have one core of 600 microns and one core of 400 microns. What can be the issue here? When the fiber is connected to the spectrometer, if you are not perfectly aligned with that input slits that I showed you before, you can have some errors due to this misalignment. And this error can be also changing in the shape of the peak, but also a shift, a wavelength shift. So what are the classical setups used for calibration, spectral calibration of field spectrometers. It's presented here, and the most used one is presented in the first figure. And generally it's used pencil type reference lamp. These lamps, probably you know, are lamps having gas. Gas, of course, has emission lines very clear, like a fingerprint. So you can measure the signal, you can associate practically what means spectral calibration. You associate to each pixel of your detector one wavelength. And having this very clear wavelength position, you can associate to the pixel of from your spectrometer. So this is the classical way to do the calibration using pen lamps, reference lamps. But practically the line lamps, depending on the gas that it's in your lamp, you have very specific lines. You don't cover the entire spectral range. You can have more lines, emission lines on one side of the range, and using another gas lamp you can have it in the other part of the spectral range. So you don't cover the entire spectral range with only one lamp. Another option would be to use for spectral calibration a spectroradiometer, and here we have developed in the lab these setups where we use the high intensity laser driven source. This is a light source, broad lamp source having high intensity. Sorry. And we have an input slit here, and a middle slit here, and an exit slit here, because it's a double monochromator. So the broadband lamp is going it's reflected to one grating, and after the signal is, the separated light is passing through another slit, and again to another grating, and is going to the detectors, which is your testing spectrometer. So practically the accuracy in spectral calibration it's done more accurate, I think. And here practically you can do the scan and the calibration, spectral calibration to any wavelength that you desire, if of course the source lamp is covering this range, and the diffraction gratings, and in this case is covering. And the sampling steps also is very important. In this case, the minimum one is of 50 microns. The issue here, like in this case, we have advantages and disadvantages. In this case, the issue can be the calibration of these lamps, reference lamps, for example, doesn't need any calibration, but instead it has the disadvantages of not covering the entire spectral range. But the monochromator can be used for the entire range, but needs itself calibration to keep this traceability of measurements. And how we can do this calibration of the setup is using similar setup. So we go back more or less to the same problem, but we will see if this issue is better or worse. So coming back to using reference lamps, the method that it's used by Ocean Optics, for example, so by the producers, it's so practically you measure the signal of this kind of lamps. You will obtain a spectra like that. So practically you will know, you apply Gaussian fit for each peak. You obtain a central wavelength, and you, knowing this center wavelength, you apply a third polynomial fit. And in this way you have the correction coefficients for the position of each pixel. So you obtain for each pixel you have the corresponding wavelength. But if you do so with one lamp, here is done with argon lamp, for example, argon mercury lamp, and here is the spectra for the neon lamp. And if you want, for example, to calibrate the spectrometer for SIF measurements, so you need to calibrate the spectrometer specifically to a wavelength that is closer to the oxygen bands, A or B. So in this case we selected the line that is closer to oxygen A. This is 763.511 nanometers. So we corrected specifically for this one. So we, in this case, just applying the feed, we obtain first this correction for this line, so around 1 nanometers. And after that we corrected, so for that wavelength we have 0 correction. And we try to, generally nobody is not applying correction for each line. So applying this correction to all the other wavelengths and doing interpolation, we added one more correction. So practically if you do the correction to only one wavelength and you do the interpolation and apply it to all the wavelengths, in this way you go closely to the oxygen A and B lines, you will notice that the variation, the deviation of wavelength is, I would say, pretty high if you want to measure the fluorescence. So it's an added value for correction. And here it's an example, for example, for the other oxygen line, you add 0.40 nanometers correction. And a solution here, for example, would be to combine 2 lamps, for example, because these are the most often, neon and argon, and to couple. And in this way you can do correction specifically for the wavelength that is closer to oxygen A, and using the other lamp to do the correction for the other line, this can be an option. But still you are not correcting perfectly for that specific wavelength corresponding exactly to the oxygen bands. And here you have different the correction, the errors that you can obtain for different spectrometers. This one is in the case of high resolution spectrometer, and this is for 2 reflectance spectrometers. And you can see that the errors are between 0.1, let's say, up to, depending on the configuration, 0.5, let's say. So, I said at the beginning that what is very important is to characterize your system. So, characterize your field spectrometer is not enough. You have to do also good characterization, and you need to have a good knowledge also on your standards that you are using. So, if you are using for spectral calibration this kind of system, you need to know what configuration is the best option for your system, for your setup. And we try to check using different configuration for slit width, input, middle and exit, and different spectral range that is close to the oxygen bands and with a minimum sampling steps. And applying the Gaussian fit, we determined for each scanning point the full width, half maximum, and the central wavelength. And you can see here the difference between different configurations. So here it's for 5 nanometer slit, I think 2.5 nanometer slit, 1.25 nanometer slit, and here it's for 0.05 nanometer slit. The difference here is not related to the lamps, it's just 2 different examples. This can be obtained for any of these lamps, these shapes. But I'm just putting here to see the difference, and these differences are related in fact to the alignment of the slit that I'm using in the beam. So practically the position, if you are just changing a little bit, very few, the position of the slit, you will have this difference. So if you don't keep your setup fixed, you can include very easily geometrical errors. So, but very good results can be obtained if your system is well fixed. And here are the results obtained in the case of spectral characterization of field spectrometers using the double monochromators setups. And you have here the results for the fluorescence spectrometer. And if you remember, in the case of reference lamps, it was a correction factor of 0.900 something nanometers, so around 1 nanometer, and added 0.40 nanometers in plus from the interpolation. Here you have the correction for the entire, for each point, scanning point. So you cover exactly the wavelength, you can cover exactly the wavelength that you need. I will say that this method is better to be used for spectral calibration, because it's much easily to find out what should be the correction to be applied. And the same thing, it's in the case of full width half maximum. So practically you obtain similar full width half maximum, because practically this is done by the system configuration. But you can find the exactly spectral resolution of your system, going exactly to the wavelength, much easily. Of course, it's time consuming, much more time consuming, but in the case of using a monochromator system. Now let's just show you some major sources of uncertainty that I found in my setups, and more details you received from the presentation of Javier and Cadmir related to this. Here I'm just mentioning it. One problem, one uncertainty that can be added to your instrument response can be due to the temperature variation, and there are two aspects here. One is related to the dark noise of your system, so it is highly recommended to leave your system to stabilized at the beginning of your measurements, because this dark signal is changing in time, not only if you are changing the time integration time, but also for the same integration time you see that it's changing at the beginning of, I don't know, for the first 20-40 minutes. So this period of stabilization it's necessary. But also another aspect, so effect of temperature variation, it's during the measurements, because practically systems that are used for SIF measurements, for example, having some thermal cooling, but this thermal cooling is done specifically for the detector area, not for the entire system. Now there are systems that are developed to cool the entire equipment, and this is a good solution, I will say. But generally only the detector area is cooled down, and this can produce some errors and wavelength shift, because the temperature, cooler or lower or higher, can change the mechanics parts, so can change the position of these components, and also of course will affect the optics. And if it's doing like that, as you saw, only a very small changing in the position of the slit, for example, which is a mechanical component, can change a lot your peak position, but also the shape. And some other problems that can appear is due to the geometrical setup. And one important thing I would say is what I presented before related to the slit position. So, here again, what I will recommend you if you do calibration, spectral calibration, so if you are sending off, if you are doing the spectral calibration in your lab of your system, and you have the system composed by spectrometer and optical fibers, and for optics, not detach it and reattach it because the calibration will be changed. And this is one reason of that is because of the geometry. If you are not aligned in the same position like in the calibration time, you can change a lot the results. So you will not know if the results are correct or not. So the conclusion, I don't know if it's necessary to repeat it because I hope it was clear. And I think that was clear that the general message that I wanted to send you is that you need very clear characterization of your system in this way, and you need traceability of your measurements, and this will get you valuable results. Hopefully.
Thank you very much. Is there any question, please?
Technical presentation. I'd like to say that nearly 15 years ago, I was using a device, Spectrometer, belongs to the icon. And also we have our own calibration system to show. When they send us a lamp, also they
You mean the reference lamp?
yes. Also they were sending the spectral characteristic of this lamp, but this characteristic including the value for each wavelength between 300 and 1100. So I would like to say only, maybe you know or...
Yes, the reference lamps, of course. I don't know if you need a characterization of this kind of lamps because it contains gas. Gas molecules has specific absorption lines, so it's very clear the position related to the wavelength value, let's say, for those peaks. The only change can be due to the aging of that lamp more, so the intensity of the peaks. And the values of each peaks, you can find it in the database of NIST, I think.
Let me ask a question. For recent spectrometers, for example, ASD, what's your suggestion for this calibration period?
Like a period of calibration. Now depends, you should have like a base system just at least to check the values, the position of your wavelengths for each pixel. So the calibration, the spectral calibration, to check it before and after if you have field experiments.
I'm talking about that calibration, laboratory calibration.
So how often you should do?
Once a year or monthly?
Of your standard equipment or which one?
Testing the device. For calibration of the device.
So for SD is the equipment that you are using in the field, no?
Okay, let me ask again.
Ask again, yeah.
You show some devices for calibration?
Yes.
Okay. I'm talking about that calibration, okay? What's your suggestion for each year, for each month?
Depends. You should do periodically, at least once per year, I would say. It's better to investigate it periodically. Eventually, in the first period, to check it time to time to see how it's changing in time. Because there are here, for example, there are different kind of sources of error that you should consider. The lifetime of the lamps. How often you use it here also, you should do these checks also in the same or similar environmental conditions. presentation, my first presentation on protocols. It was on a tree related to, it was an example of irradiance sources, and it was a very broad arms of how many sources of uncertainties you should consider. So from my experience, I would say that at least one time per year, once a year, you should check your standards, at least. But now depends on the standard, of course. How stable it is.
Maybe a quick one, please.
Yeah, that's quick. Well, thank you very much for the presentation. I was wondering if you were using helium neon lamps as well.
Yeah, it was also in presentation, an argon mercury one and then neon.
No, helium neon.
No. But in the future, we would like to use a laser.
Because it's more, a laser one. Because it's more powerful. You can close the output slit up to 10 microns.
So this could be an idea of using this kind of source. But again, generally the lasers and helium neon
it's only one pulse
example.
in that case.
Yes.
Yeah.
It's
centered in 632 nanometer. So in that case, you lose how near you are from the fluorescent part, but you get a more powerful signal for. In that case, you can close the output slit and you can get
I
a
would
better
say
signal
that also
to noise
the
ratio.
reference lamp gives you enough signal, but the problem is with the spreading.
But you cannot
of
close
the
the slits because it's a cornerstone, the monochromator. It's a cornerstone. The brand of the monochromator.
The brand now is good.
Ah.
Now it's Opto something.
Yeah,
I suggest
we're both.
you carry on about the brands during dinner time. All right, next up we will have Javier.
Do you have your presentation here?
Okay, so we are going a bit back to the problems with data and instruments, and actually, okay, where to start? No, this work started with the previous cross-section where many of us were participating, and maybe some of you actually joined it and didn't know this one, but okay, again, this was a community effort. Many people that knew a lot about many things tried to put knowledge together and to fill up some, let's say, gaps in the community. And answer some or try to answer some open questions, especially related with the sun-induced fluorescence. Actually, we tried to come up with 3 papers, as Laura already told before, and 3 of them are now under review, so we hope they will be published soon, and they will be done and made available for the community. So further questions, and I think this is also a good outcome of the previous cross-action. And if we manage to do something similar from this cross-action, would be great, because we will be gathering lot of knowledge together. To help people to measure better and to know what they are doing. Actually, our questions, or at least the questions in this work, just basically focus on the instrumentation. Is there was this review from Meroni in 2009, and since then, actually, there's not been a lot of work focused on the quality of the instruments and how actually this quality can ensure or jeopardize the estimation of sun-induced fluorescence. So, many people were jumping into fluorescence, they were doing measurements, they were using different sensors. But the point is, we know fluorescence is very sensible to some problems. We know field spectroscopy and radiometry in general has a lot of caveats and problems. And it's is people actually measuring fluorescence? Can the instruments today, can they provide fluorescence measurements, or we are just estimating biases from the instrument and so on? No? And this is very important, because when we try to use proximal sensing to estimate parameters which are related to plant physiology, the same drivers of this physiology are drivers of our instrument. temperature, solar angle. All these variables actually also modify the response of our instrument. So maybe we are making very nice papers correlating temperature sensitivity of our instrument with temperature sensitivity of vegetation, and that matches, but it's not true. And this question had not been too much solved, and maybe people doing sensors like Highplan or Flex did this analysis, but they are not published, and they are not maybe known by the community. You know? So this was more or less the question we were trying to solve. Like, do our instruments allow us to actually measure fluorescence, or we are just measuring biases and noises and making fancy papers out of nothing? No? So we tried to a bit address this question, no, with this paper. So it was not easy to answer. We needed to somehow represent what the sensor does. We needed to know how actually we can characterize this sensor. We also need to have a way to propagate the uncertainties, as Andrea explained, just propagating uncertainties to radiance. One source of uncertainty is complex mathematically, and sometimes we don't have data to do it in real situations because we don't account for this uncertainty. We don't have 30 measurements to account how good is our measurement and stuff like this. So this is not also a very easy topic, no? So we decided to address this from, let's say, from the modeling side. And also we want to know, okay, what is the impact of this, let's say, uncertainty in the radiance? How does this affect to the retrieval of fluorescence, no? And I think it was in a slide before, but let's remember, studying this fluorescence is not a measurement. This is nothing. I mean, it's the result of retrieving a model, and we have several models. So you can choose the value you want because you just have different models and you choose the one that fits your data. I mean, it's not a measurement. Radiance is a measurement. This is not a measurement. This is estimation. And we are estimating. So therefore, it's, as already saw, it's prone to be imposed, it's prone to have to be biased by uncertainties and stuff like this. And the model is not linear. So it's not so easy to understand what is the outcome of the model and what is the effect of uncertainty. So we were trying to more or less respond to these questions. No? And I forgot something. Yeah, and of course to retrieve SIG we need high spectral resolution. This also leads to lower signal, more and more problems. So the question is not easy, and it's not, let's say, fluorescence, sun-induced fluorescence is another paradigm. It's not only measuring, and I say always this, it's not the same that measuring reflectance factors. You can afford a lot of uncertainty to measure when you measure reflectance factors, but maybe for fluorescence you can afford the same uncertainties, or the same kind of uncertainties. What else is this? So this was more or less the idea, okay? We need to answer this question, let's model it. Let's model it, this way we can control what are the uncertainties, we can control and we can know things. So let's try to basically, we start from a synthetic dataset with very high spectral resolution. We simulate a sensor, we do a sensor simulator, we put in this sensor biases and responses that we know are close to reality from sensors we know, and we try to simulate how we characterize these uncertainties, and then we propagate this actually to generate, let's say, a synthetic dataset of observations. And these observations already carry these uncertainties. So then let's try to retrieve fluorescence from this dataset and see what happens. Okay, and this is more or less the idea of the paper. So as I said, we started with basically we use very simple simulation from a scope of the reflectance factor and the fluorescence, and we have this very high spectral resolution downward bottom atmospheric irradiance from MOMO, and we combine this and we have this, let's say, very high spectral resolution data that we were basically convolving to the spectral features of our sensor. This is more or less, okay, don't even pay attention, but this is more or less a bit the scheme of the sensor simulator. So the sensor was able to optimize, set up the integration time. Then we had the noise from the signal to noise ratio. We were actually converting data to the radiances. We were converting them to data numbers, and then from there again back to radiances and so on. So the idea was to simulate a bit how a sensor works. Of course, it's not perfect, and likely there are more complexities, but we also try to do something, let's say, handleable for a let's say, understandable example. We simulated the characterization of the sensor. I mean, so for this we basically use a standard that we knew. This is the raster radiometric standard. We use this lamp with the known uncertainty. First thing you know is when you look at the uncertainty values of these lamps, usually they are every 50 nanometers, and we are working with fluorescence, which, I mean, so you have to either interpolate, I mean, this is not clear, interpolated, why not? I could have fixed a linear model and that's it, no? I mean, but this is one of the problems. We are trying to deal with these things, and then the standards we have are not fit for the purpose. So, okay, this is the first problem we find, no? And yeah, by the time, and because of the data we were receiving, we didn't have actually data for irradiance, so we did this easy conversion and assumed that We could basically go from radians to P, and okay, this is how we simulated the uncertainties of our lamp. And we use this lamp to characterize the instrument data. These are some of the responses that we simulated. Some of them actually were coming for actual experiments, so we knew the response. We didn't use the response with uncertainty. We just use like a perfect response, and from there we put uncertainties from this lamp, and also from the noise of the sensor and so on, and then we generate some kind of calibration file with some non-uncertainty, okay? And we deal with we use the data from the spectral calibration, from the work that actually Laura saw before. We also analyze the changes induced by temperature in the spectral features of the sensor. We analyze the effect of the radiometric calibration uncertainties, the temperature-induced changes in the photoresponse, nonlinearity, and also we use, we analyze the effect of the directional response of the cosine diffuser. It should be a cosine, but it's not a cosine. And how to propagate all these uncertainties. Okay, we didn't want to really have also we didn't have the time, but we didn't really go to a very mathematical analysis of all the uncertainties and so on, so basically we use a Bayesian method. We generated distributions of noise for the parameters of our models, and we used this approach from this paper from Omin and Richter, and we propagated the uncertainty from here. So there is some random noise, and there is also some random noise in the drivers of the models, and there is also some random noise in the parameters of the models. And this matches, this somehow is getting on one side some random noise in the signal, but also some biases that are also some distributions of these biases. Okay? And we use, of course, a Monte Carlo model for this. We only focus on one of the retrieval methods, just for the sake of simplicity. As I said, there are more methods. Maybe we'll talk about them later. And we use the spectral fitting methods from this package published by Thomas Yurita in GitHub. And this is just the method of choice. So what did we do? We deal with the uncertainties in the calibration, in spectral calibration. So we simulated the calibration. We used some data from the paper of Laura, and we did the speed of the lamps and so on. And we also analyzed, because this is very important for fluorescence, we analyzed what was the impact of the spectral shift. It's not directly an uncertainty in the calibration, but it's something that can happen to the instrument, as I was saying, no? Maybe because of the fibers, or maybe because you try to do this with two different spectrometers, which you should not, and this can lead to this kind of problems. And in general, the uncertainties were low, according to the noises and everything we were generating. Let's not forget, this is not 100% real, but this was more a framework to try to understand these things. And also we simulated shifts. So basically what we did, we had two channels, we shifted one respect to the other to see what was the effect. What is this? Yeah. So when the shifts actually are happening simultaneously in the measurement of the two fluxes, let's say we have only one sensor, and maybe the sensor, the spectral properties are shifting through the day because maybe temperature changes, but the changes are consistent in the two fluxes, the impact isn't really large as we simulated. So maybe you can afford some shifts if they are consistent. The story changes a lot if the shifts are from one channel respect to the other. Then, of course, the residual of fluorescence is really sensitive to this, and the signal totally, the noises are above the level of the signal actually, and it's totally worthless. So this is a very strong message. Never measure fluorescence with two different spectrometers. If this is a system you are trying to develop, save money by only one spectrometer, because you will never manage to match the two things. But okay, this can happen, maybe because of the fibers, and there are also some other effects that can lead to this kind of stuff, and actually we analyze next, which is changes in temperature, not maybe in the detector, but changes in the temperature in the optical path of this detector. And maybe because the mechanical expansion of other parts or whatever, you have two different optical paths for each channel, and maybe one of them is shifting respect to the other. So actually we have an experiment from Carolina, and she was changing the temperature of the body of the spectrometer, and she was measuring some of these lamps, the gas emission lamps. So we came up with this model where from the data she was characterizing how the center of the band and the full width and maximum, the width of the band was changing according to temperature for each band, and we again went to the simulation. So we propagated all this with uncertainties and came up with these results. So again, It's not the same result if the shift occurs to both channels or if the shift is occurring separately in each of the channels. No? So if by any reason you have only one of the channels maybe expanding more than the other or changing more than the other, so there is a relative shift, then maybe the fluorescence actually is compromised. Okay, another test we did, which actually isn't really significant because, of course, the sensitivity of the sensor will change with temperature. That's why you need to wait until the temperature of the sensor stabilizes, which sometimes in the field is not possible because the temperature is dynamic out there. But for fluorescence also maybe a good message is try to stabilize the temperature of the system if you want to measure fluorescence. But anyway, we tested this to see what was the impact. Maybe this, so again, we used data actually from an article from Andy. It was not actually one of these sensors that we used to measure fluorescence for an ASD, but okay, we were thinking, okay, more or less, the response of silicon should be somehow similar. We can use this model. If someone finds or characterizes better this, they can use the same approach to test it. It's not a problem. So we tested this, and in general, we saw that actually there was not really a strong issue. Especially in the near infrared, because usually the signal is more stable there. So okay, maybe we can afford some changes in temperature for the detector, only regarding photo response. If this temperature induces changes in the spectral features, maybe actually this is what is going to give problems. Another issue or another question is the problem of nonlinearity. No? And this is very tricky because characterizing nonlinearity usually, let's say, or traditionally, for let's say remote sensing applications or proximal sensing applications, we always look at the end, at the top of the spectral range, because usually is where we find the biggest changes, and also because in the bottom there is a lot of noise. And okay, we assume that we are not going to measure them because we are going to optimize, and that's good. But when we measure fluorescence, we have deep absorption lines, and actually you have very different signals inside and outside the oxygen bands or the Fraunhofer lines where we actually want to retrieve fluorescence. This is maybe a problem because maybe the bottom of one of these lines on which we rely to retrieve fluorescence is falling more in this region that maybe we don't know so well. So how important is actually nonlinearity? We use calibration coefficients of an optic sensor. They characterize nonlinearity using a polynomial fit, and they provide the coefficients for correction. First surprise, let's say, when we simulate the data, this is just the models. We don't show here the noisy data, but this data is usually noisy. Is that actually we are not even able to reproduce the model that was given by the company. And actually there are some statistical issues with the way at least they report how to do this fit, because of course there is no homogeneity, we have a biased distribution of data, and we have more noise in some parts of the data than on the others. So maybe fitting nonlinearity models is not as easy as we thought, and something that maybe should be reviewed a bit. We didn't want to focus too much on this problem specifically in the paper, we just pointed out, but it's there. And we simulated what was again the effect of nonlinearity. No? Usually the sensors optimize, and it's always recommendable optimizing the signal, but still, as we said, even if you optimize, there are parts of the inside and outside the oxygen band that have very different signals, and this actually can lead to maybe slight differences in nonlinearity, but maybe it can be enough. So in general, the analysis and the errors were not really strong for the simulation we did. They were not really strong, so I mean, for the model we had and the assumptions we had and everything was not really strong. But we actually analyzed the effect of the responsivity of the signal was changing, and was changing before, for example, the saturation point. If we the optimization level. We assume some given recommendable optimization level for the sensor, but already before this optimization level, inside and outside band, the nonlinearity was different for the signal. So, okay, this is important, no? And it's important to consider. And finally, we went for the directional response of the cosine receptor, which is something really tricky, because I don't think it's very easy to characterize. We use data from an actual characterization. We put uncertainties from our simulation, and we try to see what was going on. No? And the point here is we have very big, let's say, uncertainties, but actually we look at the model or the changes without propagating uncertainties, we see that actually the responses are not so much biased, and actually this problem doesn't seem to be so strong for the retrieval of shift. I think there is a point, let's say, and it's something I didn't explain first. we did all this sensor model with the internal noise and so on, but for the analysis of the impact on fluorescence, we only used the uncertainty of the specific sensor model that we were analyzing. So we did not add another uncertainty. So for example, in this case, there is only noise in the downwelling radiance. And this is maybe something that in the analysis is a bit biasing these results. No? But we analyze the same results without adding uncertainty, and we know that there is not a very strong bias in the retrieval of shift. Which, okay, I mean, I'm not totally sure why, but I repeat this 3 or 4 times and it's giving the same results all the time, so I think it's right, and okay, let's say. So just for discussion, or maybe I'm trying to conclude a little bit. So we simulated the sensor, we simulated the characterization of the sensor, we added uncertainties. With a Bayesian approach, we just propagated the uncertainties to radiances and to the estimation of shift. This had not really been, or I have not seen this published before, at least for the field spectrometers and so on. So I think it's not we didn't try to give like a super realistic characterization of this, but this is rather a framework, and this is maybe a tool that should be used also in the future to address new problems, to address new issues. Can be also done for atmospheric noise, structure. I mean, this is just a try to give a framework of how you simulate and control uncertainties and propagate it and try to understand what is the impact. And this is something that can help also in the working group 4, and maybe some similar exercise for other topics can be done and try to understand what are the problems. No? What is this? Okay, so just some conclusions in general. For the uncertainties we simulated, the calibration uncertainties didn't seem to be really relevant or important, so as long as the calibration is well done, it looked like it was enough to retrieve shift, but there were other effects that were related with the sensor, no? like the nonlinearity of the temperature and so on, and in general, there are not very strong effects on shift. If you, let's say, set up properly the instrument, you optimize, you have, let's say, a good use of the instrument, there is not very strong effect, but it is very relevant the spectral shift. We knew already this from before, but still there is people, I think, that they are trying to develop systems, for example, using 2 different spectrometers, one to measure the upwelling and the downwelling radiances. And this is a very bad idea because you cannot never match and have the same, you will never have 2 sensors that operate in the same way, that have the same features, the same characteristics. So this is and also I think it's important to say that it's recommendable to stabilize thermally the sensor, no? Because we see there can be some changes, not very large as we saw. Maybe another sensor has a higher impact, but the point is also we must think that we are looking at very small differences in fluorescence because we want to separate maybe vegetation with different properties in physiology or changes across the day and so on, and so differences are very small. And if we try to compare these daily cycles or whatever, and we already have a signal which is coming from our sensor, maybe it's a 50% of the changes we want to see. I mean, it's something we didn't do here. We just moved to numbers. We say, okay, this is the error in fluorescence. We didn't look at what is the significance of this error compared to actual measurements, to actual differences between treatments with nitrogen and without nitrogen. All this stuff we are actually looking at with fluorescence. And this is something that we should also try to put in context. No? Okay, these uncertainties are small, but how small are they? No? And what can be the contribution to our conclusions about the data we have? Just to finalize, again, okay, nonlinearity, a bit tricky. We also found out about this problem with the fitting of the algorithm, the fitting of the shape. And yeah, okay, for the diffuse, there are some other questions also, and that's it. In general, yeah, I said everything.
Excellent, thank you very much. We are running a bit behind of time, in particular because I've been talking too long. Anyway, so I suggest we carry on with the next talk. If you you can talk to Javier later on. It's an excellent job. Thank you very much. And next we've got
maybe let me also just suggest and overrule a little bit more because we accumulated 1 hour suddenly. I don't know how it happened. But I mean, I invite you, of course. I don't want to force you, but I invite you to make your message a bit more compact. So maybe, if you can, that would be appreciated for all the remaining talks. That would be fair.
I'm hungry, so excellent.
If you're allowed to.
Yes, thank you very much.
We don't have other.
You want to enlarge the
Now you want to switch pages.
Yeah, but we don't have other. Because it's in PDF, right? But we don't have other.
I have it
It has to
in
be
the
like, you
PowerPoint
need
as
to
well, so
click
maybe
down.
the other speaker things will. What do I do?
If you press the key down, key,
Key on the keyboard.
on the
Oh, I see. Yeah. Oh, I see. Okay, so Laura asked me to do the presentation about this reference reflectance target we had at the RCLI in Estonia. I should say that this reference target that I will show in a few slides later is mainly the Andres Cook, whose baby, but I'm happy to be the messenger. So, in our, at the Tartu Observatory, what we have, these reflectance etalons are from these that are like the 3 centimeters big. Then we have like these spectral, and then we have these reflectance target 1 meter, 1 meter. Now in the RC lab, we use the site for a lot of validation campaigns. This was going back to French Boulder and the Chris Porova, and we also want to continue in the future. So we are interested to have like good calibration target there for the airborne missions that we can carry in the future. Now this calibration of these airborne and satellite measurements, there are the challenges with it. Like if you have the CEOs, they have general requirements for these radiometric calibration sites for satellites, which the target should have the high spatial uniformity, should be like quite bright, flat spectral reflectance, temporal invariant, and approximately like lambda shift. Now, to my knowledge, of what I read in the papers quite recent was that there was like statement that currently there are no widely accepted quality assurance methods for airborne systems, that they are just like missing. So now for this calibration for the airborne sensors, you don't need like something like these 30-meter long areas. Like you can have something smaller like parking lots or the football fields or the deserted airfields. So this is the one that's close to Tartu, that's where the strategic bombarders were placed during the Soviet Union times. Now it's deserted. Metallica will have a concert in the summer. So it's good for Metallica concert, but it's not good for your calculation of the airborne thing. Like there was a study by Anderson and Milton that were looking like how the similarly disused airfield, how much the reflectance is changing throughout the year. And they observed that the reflectance changes like during year by factor of 2. So this is not very good for your if you want to calibrate your airborne. So now in Finland, at the site at permanent, they have this permanent test site in Shokula, and they have like here these targets like up to 60 meters like big, and they are made out of these gravel. So the problem, so these are the permanent reference target they use for the calibration. But these targets, they are like outside, they are not covered, so they suffer like if you have dust events. Poland, it's close to Helsinki-Vantaa airport, so that also like doesn't help. Now this gravel is also like very strong backward scatter, so it's not like very Anderson. The shape is like very this bowlish thing. And also everything changes like when it rains. It changes your magnitude, it changes the reflectance spectra and the anisotropy as well. So what we did, or what Andres kind of like thought about, was building something like this. So it's made of the concrete. It's 10 by 10 meters. And then you can see here they are like the rails. And then we have like the movable roof on the top. So it's run by the electrical motor. So it's normally the panel is covered by the roof. And if we do any campaign there, or anyone is like interested, we move it, and then it's like covered back. So we protect it from this weather. It's, as you can see, it's visible at this bird view image, like several pixels. This is how it looks from 70 meters above from the UAV. It's in the open space. So this is the hemispherical photo, and here's like this tree, but it doesn't get like really above the 10 degrees from the horizon, so it's like quite visible. Now, as you can see, it's already this bird view, like this is from 2013, and it does not look that much homogeneous. Like the problem was, the original plan was to use this troubled concrete because the idea was that it's not glossy, that is, it has like high reflectance. But the problem is that if you put it there, like even here, you can see these things. It's very difficult to make the concrete uniform, like 10 by 10 meters. Like it appeared to be like impossible. So here you can see, here he had his the spectrometer, the Spectra Vista, and then he walked and measured the spectra like every meter. So he made that grid, and this is like how it looked. And what, like here you can't see like here in the period that much, but the thing was that the variation over this era was like 20%. So that's not very good for if you want to use it as a calibration as well. So the next step, or the idea that was applied, to put it, like cover it by this Sandalin Sandal F acrylic latex paint to make it more uniform. This is the blue line, and then when you like remeasure it, everything the same way, the spatial variation of the panel was like less than 1%, so they're actually standard bars, but you just can't see them. So that kind of like helped, like it pushed it like a little bit like less down, but it's much more uniform now, and you have like here to compare with the Zenith like one panel. So optical properties. So this is the spatial map of it. Like after the paint was applied, so the variation is less than 1%. Here's the variation with the solar zenith angle. So this is the blue band, this is the shortwave infrared. So here it decreases with the solar zenith angles like from 0.26 to 0.25, and then here the decreases are more like 2%, but seems to be like quite okay. Here's the variation of time. So the same panel measured with different sensors over 3 years. So again, like you have it's quite same. Like there's some small like degradation with time. Because here, like this, with this figure spectrometer, it was measured 2016 with actually the higher solar zenith angle of like 50, the other ones were like around like 60, but it's still like the lowest, that still like quite comparable. And then you have the variation with the height, so you measure it at the ground, like in 2014, and then you put it on like we had the Robinson helicopter, you move to 70 meters, and again the difference between what you measure on the ground and up on the top, the variation is less than 1%. Then there was brought the BRDF thing, so we measured it as well. So it has the spectrometer with the RF sensor. So we measured like the reflectance panel, and then over this calibration thing, he moved it on this boom like around like measuring the azimuth step of around like 5 degrees. And these green lines is everything like what he measured. So we can see that it's once we apply the paint, this is the forward like scattering. It kind of like increased. Otherwise, it's quite. It isn't at least this backward scattering as they have now in Finland. Then you can fit it with this analytical approximation and get it for all these things. What we did not hear about it, or what we also did, that we looked about the polarization properties of the target, because polarization is also good to know about it, like how does it differ with the view angle, with the view zenith angle, if you have to consider it. So we measure with the finished figure so spectrogoniometer that measures it, also like the polarization. And here is the linear polarization, that it's here in this backward scattering, it's like less than 1%. But once you move into this forward scattering, it's increasing with the wavelength. And here you can see like how it's like here's using different scales, but how it's like kind of like copying the linear polarization in the red band, like what we all measured and what was also did with the analytical approximation. And this is my last slide. So what? If you want details, now we have the publication, what it can be used this for. So it can be for this adjacency correction algorithm, because several pixels from the world view or the crystal like fit inside the panel. You can use it for the point square function of the atmosphere registration and the elevation reference for the radar data. With an objective of the groups, maybe some of it after some work can be used between, I don't know, develop these practical examples of application of this. Thank you. Three more speakers, so if you have something else,
Thanks very much.
All right, afternoon everybody. So yeah, this is really just going to reinforce a couple of messages that have already been, they've already heard from Javier and Laura regarding the influence of temperature on your system, particularly when you're working in the field. Anyone who's worked in the field with any form of instrument will know that temperature tends to play a bit of a role on the results that you can get. Most electronics have some sort of temperature sensitivity, and of course there's this physical sensitivity relating to the optical alignments that we were talking about. Okay, so yeah, obviously if you can have a temperature regulated environment, that's great, but that's not always possible, or you want to get out there and get measuring, you haven't quite done all that sort of thing first, and of course that's particularly the case if you're working on towers and you can't necessarily build something up there, or on UAVs, or you have mobile systems. So there's some work I was doing in Antarctica that was motivated me to think about the influence of temperature on the systems. Okay, so the system we've been using is the Piccolo Doppio one we've just heard about already, so we've heard about all the details. So in particular there's various aspects that will be sensitive to temperature, including the two different spectrometers, the input of the fibre optics, the fact that we've got a bifurcated cable, one with a cosine receptor, one without, and then the electronics of the Raspberry Pi control board as well as other things. And I was doing tests with two different fibre optic cables of two different lengths relating to the ones we use with the tower and ones we use with the UAV, just out of curiosity. Okay, so in order to characterize the temperature response of the system, we have a growth chamber, basically a walk-in room for growing plants and so on under controlled environment conditions. So you can control the temperature and the light and the humidity and so on. So in order to do this, I have a stable temperature and everything else inside, so we vary the temperature. And then, of course, I put everything inside the chamber, and that was the only option with the short cables as well, of course, so combinations. The light source is this custom-built lab sphere integration sphere with this 10-watt IHLS. I don't even know what IHLS means, to be perfectly honest. Light source is what is used in terms of, we talked a little bit about how often you should be doing the calibration and so on. So the approach that we've been trying to adopt is to do a proper lab calibration once a year, but use this Calvel sphere that is portable and can be sent out and posted out, so after campaigns or so on and so forth. Check your system with this one, and then that is linked back to the calibration back in the lab. So to try and maintain this traceability through the course of the year or under different conditions and so on and so forth. And as we're increasingly becoming aware, and Laura mentioned it, as you move your system around, take things apart, put it together, things change and so on and so forth. So I was testing that using this light source. Okay, so just to summarise the overall setup, I'm able to measure between 6 and 35 degrees Celsius across this range, these long fibre optics and short fibre optics, both the upwelling and downwelling. So set it up with one, run the whole thing, change it, run it again with the other one and so on. At each temperature step, do 90 measurements. And wait about 20 to 20 minutes or so at each temperature step for it to stabilise, but whether that's long enough or not, I don't know. That's something I actually haven't looked into and thought about. But of course, when you're out in the field, the temperature doesn't wait for your instrument to stabilise. No, it keeps changing as it wants. All right, okay, so this is some of the results. So this is the effect on the circuit board temperature, comparing the two systems. So there's not much difference depending on whether I was using the long or the short fibre optics. There's a slight difference in the temperature of the two spectrometers, there's the flame spectrometer and the QE Pro spectrometer that we use in this system. I think this has been mentioned before, but just to reiterate that. Okay, so flame, both show a positive response obviously with temperature, so your circuitry increases in temperature as you increase your ambient air temperature. The flame seems to have slightly elevated temperature relative to the QE Pro. It seems to be less buffered. All right. Of course, the QE Pro has a temperature controlled detector at around in my system -9.8 degrees, but this does increase slightly at less than a thousandth of a degree with the increase in the ambient air temperature. Okay, independent of the sort of configuration, but it does. There's a slight change in detector temperature with the change in air temperature. Okay, so this is the dark readings across the wavelength for the flame spectrometer at the range of temperatures from different setups going. So we see a decrease in dark readings with increase in temperature. It's a pretty similar responses between the upwelling and the downwelling channels. So it's pretty stable across the wavelength, but definitely the temperature response. Okay, you can see again something funny there, so don't pay too much attention to that, but this is the QE Pro dark readings, much less of a temperature sensitivity, maybe something down here, but overall there seems to be much less temperature sensitivity of the dark readings, I guess related to this detector temperature stabilisation in this system. Alright, so just summarising that, so we can take the mean, of course, because it's a stable mean value of the dark reading, shall we say, across the different ones, and characterise this dark reading response to temperature. Seem to be pretty consistent across the different configurations of the long and short and inside and outside setups. Okay, and the upwelling and downwelling for the flame, but clear decrease. And of course, as we just saw from the overall the spectra, there's not much response in the QE Pro. It's largely stable over the nearly 30 degree temperature range. Okay, so now the lamp readings. Okay, so this is the flame spectrometer. So this is a figure without a legend. So what it shows you is that the blue is the low temperature, so 6 degrees going up to the red, which is the high temperature, 35 degrees. Okay, so it's more variable up at this upper end of the wavelength scale than obviously down here, and more variable in the or more sensitive to temperature in the downwelling compared to the upwelling. Okay, that's with the long cables, so that's with the lamp source outside the chamber. Okay, this is with the short cables with the system inside the chamber. Similar response, but possibly more sensitivity at this end in this system here in the short optics. And we've seen increase in the signal with temperature in this case. Okay, this is the this is the kit. No, this is the QE Pro lamp spectra with the long cables. So it seems opposite to the flame for some reason. It's more variable in the upwelling, and you can see a more clear temperature sensitivity here across the full range of the wavelengths, and which is stronger in the upwelling channel compared to the downwelling. And this is even stronger when we look at the short cables. Okay, this is really obviously a really strong temperature response. So whether this is real or something relating to this moving things around and changing the configuration frequently during the course of the experiment, I'm not sure, but there's certainly something going on there, going up to sort of like a 25% increase or so in the signal at the upper end of the wavelengths. All right. So just the standard deviations across, also like I said, at each point we measured 90 times, and so we can look at this, how variable it is between multiple or the consecutive scans. so this is the standard deviation of that. There's no really strong apparent response to temperature in terms of the sort of variability, inherent variability of the system. Maybe something there, but overall, nothing really strong. It's more dependent on the actual wavelength itself, as you can see, particularly with the flame here, and that was apparent. It gets very noisy at that end of the spectrum. Okay. All right. So from collecting all this information, we can actually at least try and characterize some of this temperature sensitivity. So this is just basically the slope. So this is the slope at each wavelength that we measure in response to temperature across the full ranging. Other than this sort of very noisy area right up at the upper end here, so this is the upwelling, the two configurations, the short and long cables, and the downwelling. There's not, as we could see from the earlier figures, there's not much of a temperature response over much of the spectrum for the upwelling, but increasing in the downwelling as we head up to the longer wavelengths. This can be, of course, characterized with some sort of polynomial function if we want. How generic it is, of course, that's an open question. And we can do the same with the QE probe. So here we see certainly we see the opposite effect as we talked about. So here it's the downwelling channel that is more sensitive to temperature. Here it's the upwelling, and we see this bigger difference between the short cables compared to the long cables. I think this is related more, not so much to the cable length, but this connection of the cables to the spectrometer. That's probably what's playing a role here. And actually, so we have a slight negative temperature response in this system, and then a positive response up here. But obviously something that can be clearly characterized and implemented if need be, because it's a very clear function there. Yeah, that's actually it. That's all. So obviously there are temperature effects that are apparent in the system. So it's probably a good idea if you're in a position to characterize them. If you're not in a position to temperature control your system, there are differences between spectrometers. From what I've seen like this is something that I really want to look into a bit more, and also a difference between your configurations and your upwelling and downwelling channels. I'm not really sure what is underlying all these differences, but we've already talked about what can contribute to this, and these are sort of things we need to understand a bit better to mitigate against them in our setup. It's not so necessarily relative to all sorts of other uncertainties that are going on there as well. But you know, the more we can minimise errors, the better. And that's all. Thank you. So I'm hoping
Thank you very much. Oh yeah, we've got Paul next. We're gonna hear something again about the Flux box. The floor is yours.
Yeah, hello everybody, it's me again. And well, I think we all agree that calibration is important, and we've heard a lot about this, a lot about the background, and also some really interesting how-tos already, which is great because I don't have to explain so much. And now I'm basically going to take you on a little journey, starting out in the laboratory, talking about the application, actually calibrating an instrument, and then moving on to all sorts of possible field applications. And you'll probably be astonished. I always say if you hand an instrument to a scientist, they'll come up with at least like 5 different ways of using it, and if you're lucky, one of them is the way that you thought in the first place about it. So there's always creative ways of application And yeah, this is basically the second part, which I will talk about. Yeah. So again, these are the two instruments we're basing this presentation upon. And although they're different in their configuration, so the flocks you can use for the fluorescence retrieval, and the rocks you cannot, they rely basically on the same sort of internal procedure of measurements. And I want to show this to you now. Basically, it consists of 3 steps. The first of which is the optimization of the measurements. The second step would be the actual measurements of collecting the upwards facing channel and collecting the downwards facing channel. And the third step would be a quality assurance step, which is collecting the upwards channel again, then collecting the dark current of the detector, which we've also already talked about. And then you get raw data, which looks plotted something like this. In order to minimize the temperature drift, was already mentioned, the QE has a stable, temperature stabilized detector chip, but we additionally also cool the detector chamber, which keeps it below certain threshold of temperature. For the field setup, we came up with this bird and dust protection. You see the spikes there are intended to make it rather uncomfortable for birds to sit on top of the cosine and pick the cosine, which initially destroys them. We don't want that. And the down-facing bare fiber optics best are mounted on really solid field tower installations, like for example you can see one here, making sure you don't have obstacles nearby casting shadows in your field of view, because you get all sorts of trouble this way. The raw data further on is processed with this processing chain I introduced this morning. I just want to re-emphasize it's based on an open source R package, which you can also download from GitHub. Field Spectroscopy CC and DP provides a graphical user interface, and we continuously work on it. So introducing more data quality flags and also fixing some problems which occur. And basically you go from the raw data through the radiances to an estimate of the solar-induced fluorescence for the flocks, and basically you stay with the reflectance data with the rocks. Now, as we've learned, the calibration is super important, and I'd like to show you some applied nonlinearity characterizations, which we do with every instrument. So in the lab, we collect at an integrating sphere different intensities, and then map this nonlinearity response curve. And what you see here in green, I think it's this spline, then smooth through this data points. And usually our experience is that it fits quite well the nonlinearity characterization, which comes from ocean optics. There are some outliers, but of course you always get them. The wavelength calibration also was introduced by Laura in great detail, so I just cover it roughly. We also use this gas emission lamps. For our case, we have argon and krypton available, and then you get an emission spectrum from these lamps that looks something like this. in the real spectrometer, and you can derive the full width at half maximum from it, and also the spectral response curve, so to say, for the wavelength characterization, which is then the polynomial third degree, which you also get with the calibration sheet for each instrument. To finish this calibration thing up, of course, you need a radiometric calibration, which we do at an integrating sphere, also in the laboratory, and derive from this the calibration coefficients according to the wavelength, so for each pixel, basically, of the detector. Now, when we go from the laboratory to the field and want to measure SIF, lots of uncertainties actually make it pretty difficult to be sure that you really measured SIF. And Andreas Burkhardt came up with this brilliant idea of using an active LED light source as a controllable reference, so to say. So you can switch it on and off, and throughout the course of the day this was done several times, and you can see this interval of steps here, which is caused by this alternating LED. And then this already can give you some confidence, okay, you have an LED offset and you have the SIF from the vegetation. On top of that, there is the Kautsky effect, which you can make use of. So therefore, you cover the vegetation for 20 minutes and get it into the state of dark adaptation. And when you remove this cover, you get a strong fluorescence peak. And this ebbs off quite quickly within a few minutes. And this is actually one of the moments where you can really measure fluorescence, because in the difference from the baseline, you can basically see this fluorescence shape, which we've also seen today in the basics. What you see here in the corner is basically one implementation of a fluorescence panel, which you can place under your field of view of the sensor, and also control different intensities of fluorescence, like artificial fluorescence actually. Now, let's take another step further into the field. Long-term application of the flocks and also the rocks have been done in vegetation, but not just that, also in water quality and phytoplankton monitoring. People were also monitoring snow melting rate and the atmosphere black carbon actually, which causes some heating up, greenhouse effects. And so the phenology, I'm just covering quickly, this is again data also I showed this morning from France, from the very high tower, and showing some seasonal changes in phenology connected to biomass and chlorophyll content, of course because it's a broadleaf forest. We've been looking at the phenological changes in vegetation indices and chlorophyll fluorescence in grassland in Jülich. We have work in the network done by Mirko Migliavacca's group in Jena, and basically the measurements are located in Spain, in Majadas. And last year there was extreme drought conditions, and they were able to also show some nice effects related to plant photosynthesis, which is actually very similar to the work also Sebastian talked about yesterday. Basically showing different or a change in the response relationship between SIF and GPP. Similar work also has been done by Petya Campbell in the United States, measuring in corn, also relating optical properties and SIF to GPP, also showing this nice response relationship. And then we had an application of the rocks in Brazil in a drinking water reservoir where people were correlating optical properties to total suspended solids in the water. And also this setup, I think it's pretty interesting because it's on a moving boat with an extended beam, and you get the cosine receptor and the down-facing fibers over the water, and yeah, trying to make sure everything is not moving too much must have been pretty challenging also there to get good results, but the results look quite good, and getting a strong correlation between the predicted and the measured total suspended solids. And to go on with the water case, basically last year we've also been installing a flux on a research vessel which was cruising the Mediterranean Sea, and there we're able to show fluorescence emission from phytoplankton in the water. And going on to snow in the Italian Alps, basically showing that impurities in the snow from the dust settling there impacts the snow melting rate. We've also worked in the network which was mounting a rocks again on a research vessel which was traveling through the northern Arctic Sea, and there inspecting black carbon concentration on in the atmosphere. And what's pretty interesting about this again is the setup, because here you see the optics mounted on this beam, and I have a short video there for you. Basically, you see how it's moving, and this little black device here, it's also rotating so to cast a shadow over the cosine receptor here to get an approximation also for the diffuse light, and so this was a pretty complex setup with a gimbal to keep it leveled, and apparently worked quite nicely. And with this you see there is a vast variety of different applications of the instruments, and from towers to mobile applications on a ship, and all these setups of course have different influences on the measurements, different requirements again to check the uncertainties. So I think there's lots of work to be done, and I'm pretty curious about learning new things basically, and learning basically how maybe our calibration could be improved, and also how the setup uncertainties can be maybe quantified in a better way. And to leave you with this, I think this year we will put out the 30th flux. So yeah, there will be lots of different influences to be taken care of. Thank you very much.
Cool. Thank you. We're looking forward to doing the uncertainty analysis and all these things. So now to finish it off here, we've seen a lot of instrument artifacts. Now I believe that we're going to hear what is actually the impact on fluorescence.
I'm going to try to be short. That's a nice one. So my talk is mainly about different retrieval methods. Don't worry too much. And then we will go into the different retrieval methods. So for the one that don't know too much about fluorescence, basically what we're interested in this signal is because the light that arrives to the plant, some is going to be reflected, some is going to be transmitted, but the most important, some is going to be absorbed. And plants are going to use that to do photosynthesis. But even though that's why we are interested in measuring fluorescence. So active fluorescence measurement would use a modulated pulse of light and then measure a relative value of fluorescence, and then that's what we are going to be focusing in this presentation are passive fluorescence techniques which use the sunlight, and we use the sunlight to retrieve fluorescence. So when we go to the leaf level, we use the fluoride to measure fluorescence, and basically what we do is use a filter, and this filter what it's doing is cut the light in the region where fluorescence is emitted. When we go to the field and to the canopy level or field, a single plant or canopy level, for proximal section we have the flow, what have been already explained in this meeting, and also we have other imaging systems. And then of course we have hyper and we have flex, but in this presentation we are mainly focusing proximal sensing. So what we need to do to retrieve fluorescence? When we measure the outgoing radiance, what actually we are measuring is the radiance that is reflected by the vegetation plus the fluorescence. So that comes the tricky part, because when we actually get a reflectant, and that's what we are showing here, the wetland, and this is reflectant, what we normally measure is actually the apparent reflectant, which is a contribution of the reflected radiance plus fluorescence. And that is this tiny contribution over there. So we really, when we measure in the field, we are measuring this both signals. So the challenge is to be able to decouple these, to decouple reflectance and fluorescence. We will measure at leaf level, we have this filter that's able to cut the light in this wavelength where fluorescence is emitted. But we cannot put, like we can, if we want, put a big filter to the sun. So what we do is we use this natural absorption band that we have in the solar atmosphere or in the Earth atmosphere. In this presentation, we are going to mainly focus on the absorption that happen at the Earth atmosphere, which are the oxygen A and oxygen B bands. We are lucky because these bands overlap with the fluorescent emission, and that we would normally talk about fluorescent 687, which is the fluorescent that is retrieved in the oxygen B band, and in fluorescent 760, which is the fluorescent retrieved at the oxygen A band. Here you can see the different spectrums, and used to mention that the A band is thinner than the B band, and the B band is thinner than the A band, and that is going to affect our retrieval of fluorescence. So, like a really basic concept, what we do is we go to the field, we have our panel, we have our looking channel measuring the incoming radiance, and if we measure the dip of the absorption band, it will be that deep. But then when we measure the uplooking channel, so when we measure the radiance that's coming from the vegetation, we see that there is an infilling, and this infilling will be fluorescent. So basically, if we are able to measure values inside and outside the absorption band, we are able to retrieve fluorescence. This is the most basic concept, and then have been different retrieval methods trying to estimate fluorescence using these measurements. This is a list of the different retrieval methods that have been developed, but in this presentation we are going to mainly focus on the simple FLD, the IFLD, the 3FLD, and the spectral fitting method, mostly because are the ones that are most used for the scientific community. So overview of how these retrieval methods work. This is the simple FLD. So basically what we have is the wavelength, and this is the irradiance, and the wavelength, and the radiance. And what the simple FLD does is measure inside and outside absorption band, and so just requires two bands, and assume that reflection and fluorescence are constant inside and outside the absorption band. And this is the equation that's used. But as we can see here, this is the oxygen B absorption band, this is the oxygen A absorption band, and fluorescence is not constant inside and outside the absorption band. So to try to overcome this error, what the 3FLD does is use three bands, two outside and one inside, and what that is that's an interpolation to try to estimate what will be the irradiance and radiance inside the absorption band if we don't have the absorption band. And that's basically what does to, again, using the same equation, but now the point is outside, will be the value for the interpolation. Then we come to the IFLD method. Here, so the 3FLD is assuming that we have a linear variation, but again, it's not true. In some cases, might be true that what the 3FLD in some situations works more or less okay. We will see later in the results. But normally we don't have a linear variation. And that's when it comes the IFLD method. Basically what it does is use the full spectrum to improve the interpolation in the irradiance, and then to be able to estimate the apparent reflectance and then have a good interpolation in the apparent reflectance. With that, what the IFLD method does is get two correction factors to correct for the reflectance and fluorescence, and that way we can improve our estimation of fluorescence and then also the reflectance. And the next method is the spectral fitting method, which is a different approach of what we have described so far. Basically, the spectral fitting method, what it does is you have a function, that you define a function which will fit your reflectance, and then you have a function that will fit the fluorescence. In this specific study, we are only retrieving fluorescence at the oxygen absorption band. That is what here I'm just showing like a fit in the area where the absorption band is. But there are more advanced spectral fitting methods where I'm really trying to retrieve the full fluorescent spectrum. So then basically through a cost function, what the spectral fitting method is going to do is you have a function defining the reflectance, a function defining the fluorescence, and this function have parameters that define a coefficient that define this function. It's going to be playing with these parameters until you get the best match between a model radiance and the radiance that you have measured in the field. For this specific study, what we did is we used a spline function to model the reflectance and a Gaussian function to model the fluorescence. But there are different studies. For example, in the paper published by Deviations et al., they use a spline function for reflectance and they use a void function for fluorescence. Why we did this is because we tried both, and this one was the one that we used in the paper was better, and that was the one that was used by Tommy at the open source R code for the flux. So now coming to practical cases, what we did is actually Alex Dan, who is here, simulate data for the most common spectrometers uses to retrieve fluorescence, to measure radiance and then retrieve fluorescence, which are the ASD, Maya, HR, and QE-Pro, which have different range, different spectral happy interval filled with a maximum and signal-to-noise ratio. And what Alex did is simulate 16 different meditation types, combining different LAI, chlorophyll content, fluorescent efficient, etc. So we have irradiance model data, radiance model data, and also fluorescent and reflectance. So doing that, we were able to retrieve fluorescence using the different spectral, the different retrieval methods. This is the simple FLD, 3FLD, IFLD, and spectral fitting method. Here I'm showing the results for the oxygen B band, so fluorescent 687. And this is the reference fluorescent, so the one that we modeled, and then the retrieved fluorescent. And as we can see is that as we have one more thing, so the red will be the ASD, the green, the Maya, the black, the QE-Pro, and the blue, the HR 4000. And as we can see, like as we get a higher spectral resolution, our results improve, and also the best results come with the FLD and the spectral fitting method. Basically, that happened is coming back what I saw before. So the oxygen B band is really thin. So we have a broad spectral resolution. We are missing information of the absorption band, and then when we do the different interpolation, or when we assume that the reflectance and fluorescence are constant inside the absorption band, we are the error that we are introducing is quite high. Then coming to the oxygen A band, and we have the same plot, simple FLD, 3FLD, IFLD, and a spectral fitting method. And again, we can see that as we have higher spectral resolution, ours will improve. But here it's also interesting that in the 3FLD, and it's what I said before, the oxygen A band is broad. So using the 3FLD with the spectrometer with a higher resolution, we also get quite good results. So then coming to the major source of errors, we identify from our experience that there are 4 main sources of error. One is the definition of the wavelength range of the oxygen A band and B band. Another one is the selection of the solder, so this point that we select outside the absorption band. And then the interpolation strategy that we use, and then the mathematical function that we use to model fluorescent and reflectance. The one that are affecting more our retrieval is the definition of absorption band, and then on the other side is the mathematical function used to model fluorescent and reflectance that is mainly affected the spectral fitting method. So use some examples. So I say the first one is the definition of the absorption band range and the wavelength that we select. Basically, just to remember that what I am talking here is if we define that here and here, for example, is when our absorption band, the oxygen absorption band ends, and then we need to select points outside the absorption band to do the interpolation. So what we show in this example, here we have the wavelength, and here we have the relative error, which is the difference between the model fluorescent and the retrieval fluorescent. And then we show the result for the different retrieval methods. So the black is the simple FLD, blue 3FLD, red IFLD, and then dark blue the spectral fitting method. This is for the fluorescent in 687, and here for the fluorescent in 760. So as we see, like as we get farther from the absorption band, we have higher error. Basically, it's because our interpolation. So first, for the simple FLD method, as we said before, the values, the reflectant and fluorescent is not constant inside and outside the absorption band. So as we get far away from the absorption band, we are introducing a higher error. And also when we do our interpolation, as we go farther and farther, we are introducing an error when doing the interpolation. The results are consistent between both oxygen bands, and then the spectral fitting method is the one that gets less affected, because basically we have defined a function to model the fluorescent and reflectance spectrum, so the definition of absorption band is not affecting that much the retrieval. So some tricks, if you want to apply the spectral fitting, the FLD retrieval method, is that for the channel inside absorption band, don't always use a fixed value. That's a mistake that a lot of people do. Basically, what has been explained before by Javier, if you have a shape in your spectrum and you always define a specific wavelength inside absorption band, and then you have a shape, then you are going to make a mistake. So always look for the minimum value in the irradiance. And the same for the channels outside. Depending on the resolution of the spectrometer and also the noise spectrometer, you will define these points outside the absorption band, so don't use a fixed value. Try to first look to the spectrum that you have, then see where the absorption band stops, and try to choose these points as close as possible to the absorption band. Then the next error is interpolation strategies. And again, so how we do the interpolation, there are 2 factors that will affect the interpolation. It's the point that we choose outside the absorption band, and also the function that we use to do this interpolation. As I said before, we use here, for the irradiance, we use polynomial, and then for the apparent reflectance, we use a spline. But maybe your data is, you have lower spectral resolution, and then a spline a spline function basically is gonna try to follow all the points that you select to the interpolation. So you have really noisy data, or your resolution is too broad. Probably you will have like a big jump over here. So we will like a jump in the absorption band, and then you will introduce an error in the interpolation. So before getting a code from someone and then just running your data through the code, plot the results and check that the interpolation that you are using and the point that you selected are the right ones for the data for the characteristic of your spectrometer. So this is, for example, an example. So we have our data set. This is the irradiance, and this is the apparent reflectance. So the first thing that I did is I'm just going to select all the points to the interpolation that they are outside the absorption band. But if I do that, the interpolation is going to try to follow all the points, and actually I'm going to be making an error because I'm going to be doing an overestimation of the irradiance and also the reflectance. So what I did is choose only the local maximum, and then with the local maximum, we improve our interpolation. Again, this the effect affect both the IFLD method or the FLD method and also the spectral fitting method. Because for the spectral fitting method, you need to have like a first interpolation at the apparent reflectance to then run the cost function. So if you make an error there, then you will have also an error in the retrieval. But because go through this cost function, probably the error will, where the error gets like mitigated, get lower, because the cost function will kind of like correct the initial error that you make doing a bad interpolation. So some tricks is again adapt your interpolation to your data. So don't use repeating the same again, but I think it's really important. Don't trust any code that someone gives you. If you have your own spectrometer, plot your results. Use the local maxima to interpolate and plot your results to be sure that what you are doing makes sense. And then the last thing that we didn't do that on the paper, but it's really important. I learned that working in Julius with Andrea. He make a really nice setup to validate the flux. Is once you have your instrument characterized, you have your retrieval method implemented, do some validation. So before going and start measuring vegetation, take targets that are not fluorescent target, and then measure and then retrieve and see the fluorescent value. If you get in a non-fluorescent target, like can be like a gray panel or soil, you get positive values of fluorescent or really negative values, there is something wrong. So before trying to use fluorescent to understand the physiology, do this kind of validation. So just conclusions. In this study, the HR and Q-Pro spectrometer combined by the IFLD and the spectral fitting method approach were the most reliable for the retrieval of fluorescence. The spectral fitting method was the less affected by the wrong definition of the absorption spectral windows and the interpolation strategy. And then some tricks, just repeating again. I know that I say that a lot of time, but it's really important. Retrieve fluorescent, as Javier said, is not the same as measuring reflectance. Adapt the retrieval method to the characteristics of your measurement systems. Plot the results so you know that what you are doing makes sense or not. And then, again, before trying to interpret the fluorescent signal, do a good calibration and clarification of your system, and also a validation of your retrieval method. So with that, as Javier said, these three optimized papers were the work of the community, like a big effort of all of you. So a big thank you to you all for your help and support in the paper. And last, and not important, do the question. I guess that you want to leave, so the question.
Yeah. So before you try to Skype off here, I had the intention to treat you and to another question here. I'm not going to be as cruel. Just to repeat what we want to do, we want to know what you guys do about uncertainty, traceability, what instrument types you use, and what calibration characterization you're doing. And we've seen this before, we've got the different levels, and we want to know about traceability. I'm going to send around this survey monkey, and it should be all self-explanatory, hopefully. And you get an email from me, and I'll have to badger you at some other point. And with this, I'd like to apologize for running a bit over time here, and I'll hand over to our boss for further details.
And I'll hand over to our co-chair.
I was given the honor to close this program, and we went way over time, so I will make it really short. We all still want to see some sunlight if possible. So I want to thank you all. I want to thank all the speakers, the organizers of the working group, all the people that are still here that managed to stay so long. I think we started with 60 people for these 2 days, and we are still here with more than 40. So congratulations to you all. Maybe a few small announcements also. Please sign your attendance list, otherwise you will not be refunded. And also, I think we are going to skip our discussion. No? We want to go outside to the restaurant. Or
should we improvise at least one conclusion sentence, or I mean, can we, or we skip it entirely? I mean, yeah. Okay, we skip it, and
yeah,
we can have it while eating, maybe.
Yeah.
For the presentation, is now password protected part on the SENSECO website. So if it's fine with everybody, I would copy the presentations which are on the laptop and convert it to PDF.
Does everyone agree? Is there anyone who doesn't like to have his or her presentation to be on the website? Or if that's not the case, I think you have the full approval. Right. And then, are you done? Are you okay? Or then just a final remark. So tomorrow, I don't want to be impolite and kick out people from tomorrow's meeting, but apparently I have to. So post office asks us to be very strict. Tomorrow in the MC meeting, only maximum 2 people per country may attend. So that is normally the management committee member, or if one member is not here and you're replacing as a substitute the other member, then of course you may come. But we can only have 2 MC members, respectively substitutes per country. Yeah. Otherwise we would be violating the cost rules, and we cannot have anyone who's not an MC member a substitute in here. So I just want to, not that you're coming tomorrow and then, you can't enter and then, yeah, so have that. And please, if you are here to represent your country, please come, because we, in order to be functional, we need to have, how many? 2/3 or 60%? 2/3 of the member countries have to be present, otherwise we are not functional and we are not, we can't approve anything.
Yeah, but also for the people that want to catch the bus will be leaving from here, so not from the hotel also. So people that will still join the bus at 11 o'clock, he will leave sharp. And so I guess we just meet here outside and before meeting to the bus. Also for the restaurant this evening, we will leave from 20 to 8 from the hotel, for those who are at the hotel. And we walk towards the restaurants. That's it for today. Thanks a lot.
No photo.
Oh, damn it, it's not so dark. You missed on that.
What is this here?
Can you take the photo now? Clement is
it was a joke.
Shall we go outside for a photo?
Is it still possible? Okay, why not?
Okay, let's go. Let's go. Yeah.